But this evening's guest speaker is Professor Jean Armstrong there from Monash Uni, and you can read all I can, it's too small for me.
Don't worry about it.
Pass it over to Andrew to complete the introduction. But thanks very much for giving up your evening.
I'm happy to introduce myself if you want. Okay, yeah, so first thing that's probably immediately obvious is that I've got a Scottish accent. So 37 years in Australia has had absolutely no effect on my accent. At all, yeah. So
Another problem.
So anyway, I took some poetic license. This is an adaptation of a talk I've actually gave at Victoria University, and I thought, seeing as my group in Australia and Monash were the sort of leading the world on a couple of things that I thought you might be interested in, so I thought it would be worth talking about. So I'm going to talk about visible light communications and visible light positioning. Okay, I thought you didn't give me an introduction, so I thought I'd give a bit of an introduction myself anyway, so you didn't
The reason
need
for that was I couldn't read it.
Anyway, well, none of that's on the information. I actually started my career in Scotland working for Hewlett Packard, and I actually, in Edinburgh, South Queensferry, yeah, and I started out designing surface acoustic wave oscillators and working on the microwave link analyzer, which a few of you look old enough to have come across. And then I came to Australia to work at Melbourne Uni, and then I've been at Melbourne and La Trobe and now Monash. Now, I'm probably actually better known. The visible light communications is quite a recent thing. I've actually did lots and lots of work on OFDM, which you've probably all heard about. OFDM, orthogonal frequency division multiplexing for radio systems, and I was quite well known in that. But I got a paper to review a few years ago which was about transmitting data from light, and I thought that's a really interesting idea. Why don't they use OFDM? I mean, OFDM is the solution to everything, so why isn't it the solution to this? And I was told that, well, clearly you couldn't do it or someone would have done it, and I thought, well, that's ridiculous. Of course you can do it. There's so many degrees of freedom in OFDM. So I came up with an optical OFDM, and I've got the paper on that if you're interested. And from that I've gone on to visible light communications and visible light positioning. But so as I said there, am I a radio engineer in disguise? So if you want to ask any specific questions about how it's different, because optics is all smoke and mirrors, I'm happy to think. So that's my background. The rest is what I'm going to do. So I'll move on to the next bit. Okay, so I'm talking about visible light communications. So here I've divided types of optical communications into a square. So we've got the frequency along the top, either infrared or visible, and either optical fiber communications or optical wireless. So conventional optical fiber, what all the internet's backbone is glass optical fiber using infrared. There's actually quite a lot of now plastic optical fiber is becoming quite, and it uses visible light. There's lots and lots of wireless using infrared. Someone was mentioning about a cross between buildings. So here we've got between buildings, and that's a laser at one end, and I'm sure some of you remember ERDA. It still exists, I think, but no one uses it to connect between computers because it's horrible. Wireless remote control. So these are all optical wireless, but using infrared. But what I'm mainly been concentrating on recently is, so this area, visible light communication. So using visible frequencies to communicate wirelessly. Anyway, so optical wireless is now a really hot topic, but it's not actually a new topic. I pinned some pictures off the internet. You could say semaphores, optical wireless communication, or smoke signals is also optical wireless communications. And apparently Alexander Graham Bell, who you all know, of course, is Scottish, invented the photophone. So it's not a new technology, so why all of a sudden has it become topical? Well, first of all, because everyone wants to use the internet all of the time with lots of data rate. sorry, RF has got limitations. There's whatever, no matter how clever radio frequency engineers are, there's a limit to the spectrum, even using MIMO. But really, one of the reasons is opportunity. Visible light, optical transmitters and receivers are absolutely everywhere. You might not recognize them. Well, you probably do, because you're all communications engineers or interested in communications. But the first thing that sparked my interest was white LEDs. So I don't know whether these are LEDs or not, but people have shown that out of a conventional white LED designed for lighting, if you're clever about it, you can actually transmit about a gigabit per second. So you can get a gigabit per second out of your lighting LED, standard lighting LED. So there's LED traffic lights. People are using them. Tail headlights, you might think they're headlights. You could think of them as optical transmitters, same tail lights. Camera is an optical receiver. iPhones are a transmitter and a receiver. LED displays. So this is and this one at the bottom is a bit of a joke. Because this is actually Tiananmen Square, and there was a invitation-only thing where Rick Roberts is the guy from Intel, and this is the guy from Japan and we were invited there, but we were shown around Tiananmen Square, so it's not a very good photograph, but there's a huge, 20-meter by 10-meter LED display, which we were discussing its potential as a multiple output optical transmitter. So anyway, what I'm going to talk about is mainly on the positioning and using lighting LEDs, but the research, a lot of my research is quite fundamental, so it applies quite a lot across all of the disciplines. Okay, so this is the kind of thing that my research group has been looking at, the situation where you've got, so this is a room, you've got LED lights, and you've got some kind of receiver. So here, if you were transmitting from these lights and they were LEDs, you could have, I don't know how many, you've got 16 of them on or something, you've got 16 transmitters up there, and receiver down here. Okay, so basically you transmit from your lights. You've got to, the reason why LEDs are really useful for this and fluorescent lights aren't is because you can transmit much higher frequency signals. It's got to be high enough so that it doesn't annoy you, which creates a problem in some issues, but basically the systems transmit very high speed signals, higher than the flicker. You receive signals from one or more lights. So if I had a receiver here, depending on the design, the field of view of the receiver, you could potentially pick up signals from all the lights directly, like I said. Yeah, so what are the advantages of optical wireless? Potentially you've got a huge bandwidth, but not as huge as a lot of people think. It's not really the optical bandwidth because of the properties of LEDs. It's actually the bandwidth of the modulation, so how fast you can change the light coming out of your LED. So no licensing.
Only at the moment. We'll like text it.
You've got cheap and simple transmitters. You've got an LED. So even undergraduate students, even not the best undergraduate students, can design transmitter system quite readily. There's no interference issues. It's safe, secure. You shut the curtains and people can't eavesdrop. And this is probably the one that appeals to you. People are used to transmitters being located in prominent positions. I mean, if you try to put radio antennas in all the positions in the lights in this room, I think you might get some objections. But people are so used to lights that lights are on ceilings, you don't need to worry about it. So they're everywhere. Fault finding is easy. So what you see is what you get. It's not like your Wi-Fi, you can't work out why it's not working. If you could see the light, it's working. So lots of opportunities, but there's also lots of disadvantages. Okay, light travels in straight lines, approximately. So you've got a problem. As long as you can see a light, it's fine. But if you start trying to receive somewhere that you can't directly see a light, your data, it's not impossible. You actually do better than you might think. But you can't your data rate goes down a lot. So if your line of sight to a transmitter, you can typically get signal to noise ratios of 60 dB, things that radio engineers often dream of. Okay, but as I said, it's all smoke and mirrors. The signal to noise ratio falls off as the fourth power. Okay, not the in free space. This isn't, you know, Free's law, whatever the one about the mobile phone is. This is in free space. It falls off as the fourth power. The signal to noise ratio are much lower. So as I said, if I've got a receiver here, I can see a light, then I'll have a really good signal to noise ratio. If I'm under here, I'm not down to nothing because there's still some light down there. You can actually do better than what I think, but it's very dependent. Okay, all sorts of funny effects. If you're only using the diffuse path, so the reflected path, you end up with a bandwidth that depends on how big your room is. So the bandwidth of a big room is of the order of tens of megahertz. It's the bandwidth, it's the interference happens at the baseband frequency. So as I said, it's all smoke and mirrors. The bandwidth depends on the size of the room and the how. So if you've got very reflective walls compared with not. Okay, the big problem is interference from ambient light, and that's from completely, well, it's not just the light, it's something called shot noise. One of the things people say is it doesn't work in total darkness, which is almost not true. With no ambient light, you require very low transmit power. So one guy at Boston showed that if the background light was at the level of one star, you know, one star in the sky, your transmitter only had to be transmitting power at the level of one star in the sky. So if you want to have your, you know, show your videos in the dark, you can get enough power out of the you know, the indicator lights that are all over the place, and now I can't see one, but they're bound to be an yeah, there you go. Yeah. So it's all very different, and it's because of the different mechanisms of interference and noise. Okay, the other thing that is, in my opinion, probably a more immediate prospect because it doesn't involve so much standardization and you can have standalone systems is visible light positioning. So the same thing, you're transmitting signals, but the receiver works out where it is in a room. So, you know, if each of these lights transmits a signal giving some information, and what information, it depends on what you want to do with it, you can potentially work out quite accurately where you are within a room. So it contains information. You receive signals from lots of lights, and then so your receiver could, for example, be a smartphone. Required accuracy depends on the application. And actually, with my colleagues at Monash, we've got the paper in the top journal that describes all of this. We did quite well. So I've got a copy of that if anyone is interested. And also, I should have said it, I've actually got a web page that got links to most things. That was on the front side. So basically, it's like a GPS system, but using the lights, not satellite. And obviously, it doesn't work outside. It's complementary to GPS. Okay, so I hope I've convinced you about what wonderful opportunities it is, but optical wireless is very different. So basically, and I'll get onto this, you forget everything you ever knew. Everything that's common sense in radio doesn't work. So it's actually quite interesting. So here's a typical transmitter. Okay, typically you've got an electrical circuit that generates whatever signal it is you want to send, and you transmit it. I'm only thinking about LEDs, so forget about lasers at the moment, but your transmitter is an LED or a laser. It goes through some optical channel, and for me that's the air that we're talking about. We receive it by a photodiode, and then it's converted back into the electrical domain. So what did I say here? So I've got a LED or a photodiode. Okay, so in the electrical domain you can have positive voltage and negative voltage. You can have FM, AM, OFDM, whatever takes your fancy. But in the channel, if you use a LED, the signal's represented by the intensity. So that's the instantaneous power, which can only be positive. So you've got to code your signal with something that's only positive. And once you get back to the receiver, you can be back to positive and negative signals. But the curious thing is that the dominant noise is something called shot noise, which is added in the electrical domain. So your signal's all got to be positive, but your noise can be positive and negative. Okay, so a little bit about your transmitters. And stop and ask me any questions if there's anything that people are specifically not understanding. Is it all making sense? Yeah. So there are basically two ways of making white LEDs. One is to have a red, what is it, have we got? Blue, red, and green LED. So here's the optical spectrum. You transmit blue light, yellow light, green light, and red light. And by getting the proportions, it makes it look white to your eye. Or, there we go. The way that most LEDs work is that it's actually a blue LED in the middle with a phosphorescent coating around the outside. So the blue light hits the phosphorescent coating and makes all the yellow lights, and it looks like white. And when you get either, if you buy LEDs that are cool, neutral, or warm, that's by adjusting the amount of phosphorescence. Okay, so that's what they are as lights. What about as data transmitters? Okay, and this work, the person who did most of the work initially was, or there are two of them in Germany, but they found that typical, I might have got this later on, you can modulate the three LEDs separately and detect them separately if you use optical filters. Okay, an optical filter can be a bit of coloured glass. You can call it an optical filter, but a bit of coloured glass, or you can be more sophisticated. But you can modulate each of them, and people have measured them. So you've got about 15 megahertz bandwidth times 3, so you've got quite a lot of things. Most LEDs are the phosphorescent ones, and the same person showed the bandwidth of the blue LEDs about 35 megahertz. I'm not quite sure why they're different, but anyway, these were measurements on standard lighting LEDs. The problem is that the phosphorescent coating only goes at 2 megahertz, although it's much faster than I would have thought the phosphorescent coating. So if you modulate your blue light, your blue LED inside the phosphorescent coating, you can get the blue light to go at, what have I got, up to 35 megahertz. They say they're more typically 10 megahertz. But the phosphorescent coating will only go at 2 megahertz, which is probably 2 megahertz faster than you thought it would go, but it's at 2 megahertz. Okay, so you actually need to, there's different ways of doing it. You can either filter out the yellow with a blue filter in the receiver, or so you've got a trade-off between bandwidth and power and interference that actually our calculations and other people's calculations show that you're actually best to just use the blue and throw away the yellow, because it creates more problems than it's worth. Okay, so what have I got here? Right, this is where it all gets even more smoke and mirrors. Okay, first of all, the system is linear in intensity. So the intensity of the transmitted light in an LED, so the power out, the optical power out is proportional to the current in. So power is proportional to current, forget all that I squared R. Power is proportional to current in an LED. So the current, and the photoreceiver, the opposite happens, that the current out of the photoreceiver is proportional to the intensity, which means that what you put in, so the current out here is proportional to the current in here, so that's all nice and linear, that's what you want, apart from impulse responses to people. You can only have an impulse response that's real and positive, and that upsets a lot of the things that you're used to thinking about from radio systems. Multipath fading occurs at baseband frequencies. So if you've got a radio system and you're going at a gigahertz or something, you move a little bit and your fading changes. Optical frequencies, your wavelength's very small, but it's actually at the baseband frequency rather than so you get all sorts of peculiar effects. Okay, multipath fading occurs at baseband, not optical frequencies. And I've said this is good and bad. It's good because it's much more robust. You don't change a little bit and the thing drops out. So as long as I'm still within sight of whatever it is that's transmitting, it's not going to make much difference unless someone walks in the way, in which case you've got a real problem. So Doppler's not a problem because the multipath is at baseband frequency, so you're never going to be moving so fast in a room that is. But it's bad because you can't get diversity. Okay, the hot thing in wireless communications is diversity and MIMO, and it's very difficult to get diversity because the different, if I choose one light there, the difference from receiving it here and receiving it here is negligible. So it's quite difficult to get diversity. So conventional, as I've said, RF, defining conventional as radio frequency, spatial multiplexing doesn't work very well. Okay, so what have I said here? Why RF engineers need to forget everything you ever learned. Okay, and this is quite a challenge because lots of theoretical people who have published lots of papers in radio RF systems are now trying to reinvent the papers in optics and optical radio and optical wireless, and it doesn't work, and there's a very limited number of people who can actually review the papers and say that they don't work. So it's, it's a challenge for those of us who are working in the area. So transmitted signal must be non-negative. The average power is equal to the average of the signal. Forget, you think of power as being V squared or I squared or whatever. It's not, because what you're transmitting, the signal you're transmitting is instantaneous power. The average power transmitted is the average of your signal. And a lot of the literature calls that optical power. The noise depends on the total light reaching the photodiode. So the worst possible situation you can have is your receiver sitting on a sunny windowsill because it's getting lots of background light, which creates shot noise. So shot noise is added and data is detected. So you're limited by the optical domain, which is limited by the average of x of t, but your bit error rate depends on the average of the square. So in radio systems, you're usually limited by the transmitted power, and your bit error rate also depends on that power. But here you've got the limitation on one thing and the performance depending on another thing. So that's what I'm saying. There's a limit on the mean value of the transmitted signal, but the bit error rate performance depends on the mean square value. Okay, so what am I saying? What are the main challenges? The obvious one is, what about the uplink? Okay, I can get data from up there to down here, but what about the back way? The current thought is that what people would do is you would have visible light communication in the downlink and Wi-Fi in the uplink, and the way that Wi-Fi works, that immediately clears up quite a lot of your bandwidth. In fact, probably more than, because typically people are downloading more than they're uploading. Sorry? Yeah.
Crossband.
Yeah, so you're down at the optical. I mean, this is all very new. No one knows what the answers are, apart from probably the answers OFDM. But that's, so what modulation techniques should you use? Right, other really tricky things, and this is people are really struggling with, is the real point about using LEDs for lighting is they've got to be energy efficient. But how do you, it's actually, in some ways, it's difficult to get a good communication system and an energy efficient system at the same time. How do you do things like dimming? How do you make it work for different ways? And how do you separate? So if all these lights are transmitting signals, are they all transmitting the same one? Or if they're transmitting different ones, how do you separate them? So it's really fun, actually. It's a really fun area to be in because very few people have done the basics. So you get the opportunity to do the really fundamental perhaps really easy things, leave the harder ones for later. So what has my group been doing? What have I been doing? I said at the beginning I came from an OFDM background, so I've been working a lot on modulation, and I'll talk about that. How do we get reliable transmission? How do we get MIMO? So lots of different things, lots of interesting things. So modulation techniques, so that's really where I came from. So because I came from orthogonal frequency division multiplexing, and I was told that you couldn't apply OFDM to optics because that was the perceived wisdom in 2005, I was determined that you could. So how do I create an OFDM signal that's real and non-negative? Well, the real bit's not that hard because ADSL modems do that all the time. ADSL modems effectively use OFDM. But how do you get the non-negative? So you've got a signal. So you've got a signal that goes positive and negative. How do you make that just positive? So you've got something that goes from plus 2 volts to minus 2 volts. How do you make that go positive? That's what everyone else said, but I had done a lot of work on clipping of OFDM signals for wireless systems, and I knew that clipping wasn't as bad as people said it was. So my answer was you chop off the bottoms. Okay, so you can't just chop off the bottoms because you get interference, but if you only use the odd frequencies, and this is really sort of high order maths, odd plus odd equals even, odd minus odd equals even. So if you only use the odd frequencies, you can get all the rubbish to end up on the even frequencies. So I came up with a new scheme, which I've called asymmetrically clipped optical OFDM. So we did some simulations and that worked. So then the next question is, how well does it work? So this is the diagram that is based on a diagram that a lot of people were using at that stage, so forget the OFDM ones. People had looked at on-off keying and pulse position modulation, things that people typically use for optics. And the way they were plotting at that time was normalized bandwidth against bit rate. So this is low data rates up that end and high data rates up that end. It's sort of back to front from what you'd expect, and we've since more recently turned our graphs the other way. This is how it was done by the optical people before. On-off keying was considered to be the norm. That's what one used for optics, so everything was normalized to that. So I did some simulations and plotted this graph, and down is good. So not only had I come up with an optical modulation scheme that worked, it was better than anything else anyone had ever come up with, tried to come up with a good modulation scheme. So I spent a long time trying to prove myself wrong, and other people have tried to prove it wrong, but it turns out that it's right. It seems completely counterintuitive that you could throw away half your bandwidth and still end up much better off, and it's basically because of this property that, we'll go back to, it's because of this. Because you want something that's got a very big mean square value, but it's got a very small mean value, and it turns out that the new ACOFDM works really well. So I did spend quite a lot of time with my postgraduates. Okay, if I had invented something that was down here, what else was lurking down here? Were there other even better things in the corner? And one of the other things that's strange about Shannon's theory, as it's normally known, doesn't apply. So there is no known capacity, closed form capacity solution. So we did, with a postgraduate called Zhai Li, we did quite a lot of work and actually tried to calculate the capacity and how close to it. So there are other things lurking down here, and actually people have come up with better. They've improved our ACOFDM. They've shown you can do better by adding on to it, not by changing it. But so that was really quite exciting. We've had a lot of fun with that. And we've asked what the capacity is and how close to capacity is ACOFDM. So I also, Zhai Li, who was a very good postgraduate student, I also got her to calculate, because one of the things that people kept saying to me is, well, it works all right as long as you can see the lights, but if you can't see the light, it won't work. So I got her to calculate from first principles, if all you've got is the diffuse light, so if we're down here, what's the maximum data rate, theoretical data rate that you could get out of a system with, I think we went for 1 watt transmit power, it might have been 4 watts transmit power. And it ended up at 70 megabits per second. So even, this is theoretically, no one's actually ever done it, but theoretically you could show that even if you don't have a direct line of sight, you can do pretty well. Okay, so how do you ensure reliable transmission? You need a receiver with a wide field of view, and actually I forgot to get my show and tell out, but I will do that later. So, how do you take a picture with a wide field of view?
Fisheye lens.
How does a fisheye lens work?
Very well.
No. Well, I started looking at fisheye lenses and I thought, this is all too hard, I can't understand this in the timeline that I had to write the grant application. So I did a bit more of a literature search, and I came across a 1922 paper of someone trying to take a picture of cloud cover. So picture the whole, and he used a hemispherical lens. So we got ourselves a hemispherical lens, the wrong way up, as all the optical engineers kept telling me, but it's not the wrong way up, and showed that you could get so this is, I've got pictures, yeah, so here's our hemispherical lens. This is taken it was actually in the Student Union at Monash, a place like this with lots of things. You could see that with the hemispherical lens, you could actually project images of lots of lights. Whereas if you just use an ordinary lens, so that was interesting, and we've got some papers on that. But a hemispherical lens is pretty bulky, so why not use a Fresnel lens? Why not use a Fresnel lens? Because it was too hard to analyze. So we went for prisms and how well you could do with arrays of prisms. And so with a postdoc called Tom Wang, who's working for me now, so the poor guy came with a radio frequency background, and I said, okay, it's nice to have you here. What I want you to do is analyze a hemispherical lens. So he rose to the challenge, and we've done quite well with that. And then we've gone on to these other structures. So basically what we're trying to do is we're trying to get multiple input, multiple output. We're trying to have something where we can put, say, this one. So each dot represents a different transmitter, so we can separate the signals from different transmitters. So that worked well. Now, how to design an energy efficient system. Okay, for energy efficient systems, we want the LED to be fully on or fully off. So one of the problems is, okay, we've got these beautiful signals that have got really nice things. You've got these energy efficient LEDs, and what you're going to do is try and stick a big high power analog linear amplifier behind it. It's not going to work. So we started thinking about how you could be more energy efficient, and actually most LEDs, increasingly they're being made of arrays of LEDs. So instead of switching controlling all the LEDs with one signal, we basically switched. You want a big light output, turn on lots of LEDs. You want a small output, you've got to do it very fast. So that's another thing we've been working on, and a mixture of final year projects. And so we're doing most of this on an oily rag, a sniff of an oily rag. So you can generate the analog signal, but you get all sorts of funny effects that your signal actually depends a little bit on where you are, so relative to the transmitter. Okay, so do you want me to keep going about visible light positioning, or you had no? Yeah. So the other thing that I actually think the visible light positioning in some ways, it's more immediately commercializable because you can have a standalone system. You don't need communications to your light bulb. You can actually potentially it can be just as simple as changing your light bulb if you've got clever light bulbs with something in them and there is potentially a huge market. There has been one report written quite recently, these people who do commercial reports. I haven't got the report because they wanted to charge me $10,000, but I have read the paper that refers to it that says the market for supermarket only, just ones using your mobile phone, is something like $5 billion a year. So what they're talking about is you walk into the supermarket, you're standing in front of Wheaties, and the system detects you're standing in front of Wheaties and streams data, adverts about, Wheaties are on special or whatever. I mean, it's horrific in some ways, but you can see that it's possible. So here's a nicer version. This is just an improved version of the kind of thing that lots of public places have, where you put the headphones on and it tells you what, you press button 1 if you're standing in front of the Mona Lisa, or press button 2 if you're whatever. So the same kind of thing. Now the reason, I've got the copy of this paper, so this work was done, probably got it somewhere here, right? So this paper we wrote, and I've got a couple of copies if people are particularly interested, but we actually went through and considered what you actually needed, what data needed to be transmitted out of the light. So in this example, if I'm being told about this artwork, all the system that needs to know is that I'm standing in front of that artwork. It doesn't need to know where I am in the world or even where I am in the room. It just needs to know that the nearest light bulb is the one above the artwork. So there just needs to be enough information to work out what the closest light. So a simple receiver, and that was one of the things we considered. Another example, I mean, you can come up with tons of examples, but this is one where are we going? I'm trying to get the laser to come on without, So this is, and Amit Scargioli, my colleague, did all these nice diagrams, but basically just one example of using it for asset tracking. You can imagine that in a hospital, someone wheels or same the supermarket trolley, someone wheels the patient into a room, offloads the patient and doesn't take the wheelchair back to wherever it was supposed to come from. So you could design quite an easy system that the wheelchair, it has to know which light is closest, but it would use some other technology, use radio systems to say, I'm in ward 33, come and get me, kind of thing. And so this was a special issue about standardization. So we were saying what the signals had to have so in this case, you have to have a central database that knows which light's in which room. But once you get to more subtle things or more precise things, okay, these are some nice little mobile robots that my colleague Amit Scargioli has had undergraduate students build up over the years. So suppose we want to accurately calculate where they are. You need to be able to receive signals from several lights, and you've got to be able to calculate from that where it is. So then can you use, it's like GPS, can you use triangulation or can you use trilateration, or what works? Okay, there's a number of ways that you can do this. So there's a number of positioning techniques. Received signal strength. So I've got on the next slide. Anyway, received signal strength is typically what Wi-Fi systems, there's Wi-Fi positioning systems, and what they do is they detect how strong the signal is from all the transmitters. Well, they're fundamentally limited because, there's lots of things there's the relationship between distance and power might not be that simple. You can do things like time of arrival, which is what GPS does, but that requires atomic clocks in all your transmitters, which is not going to happen so we concluded that angle of arrival was the way to go. So what have I said? What method is best to use? So most people have been using received signal strength, and I reckon that's got no hope at all. I mean, if you've got a dirty light bulb, you're upset your received signal strength, or a moth in your thing. What happens if it gets dim? Time of arrival isn't going to work. So, although when I put in my grant application, I got one of the assessors writing back that I couldn't possibly get accurate positioning out of an indoor system using things because it didn't have as great a bandwidth as GPS, therefore I couldn't possibly do better than the GPS system, which was, so we actually have calculated how well you can do using time of arrival, just so that if we get that silly assessor again, we've got the answer. But it's not very, well, the answer is as much you can get to within centimetres, partly because it's much higher signal to noise ratio, and also because you can average over, it's very stable. I mean, nothing that you can average. So, but it's still a silly way to do it, even though we've got the theoretical paper showing how accurate. The real way to do it is angle of arrival. So if you can tell which direction all the lights are, and that's not going to change if your light gets dirty, or it's not going to change much. It doesn't depend on whether you've got your lights dimmed, but you need receivers which have got angular diversity, which gets us back to where we started from. So a lot of our work has been about how we get very accurate MIMO receivers with angular diversity. Okay, so what, I can tell you a little bit about what's going on around the world. It's a little bit out of date. The world speed record, all of them use OFDM. So she got, she was Jelena Gruber, she's now Jelena Vucic, and she's now stopped doing work because she just had a baby. But all of the systems use OFDM. She got 513 megabits per second out. This is a few years ago, people have done better. But the way they do it is a bit like ADSL. You put, so this is frequency along here, and this is number of bits per subcarrier. So it's like, I don't know if you know how your ADSL modem works, but all the data goes on the low frequencies where you've got a good signal to noise ratio and much less on the high frequencies. She used a blue optical filter. So with the RGB ones, they had different bit loadings on each. So lots of different things. Guy at Oxford, Dominic O'Brien, he's done stuff on diversity receivers, but his tend to have, she does lots of nice hardware stuff. So there's probably half a dozen really good groups around the world. We're all doing slightly different things. Who have we got? Harold Haas, who people have, he was actually on the science show as well. He's now in Edinburgh. He's done, well, one of the interesting things is that they're all doing work on my modulation scheme of ACOFDM, which is quite nice to, I mean, as a communications engineer, having your own modulation scheme is pretty exciting. Rick Roberts, the person in the photograph in Tiananmen Square, he works for Intel. He's been doing things about measuring distances between cars, so you can tell whether you're about to crash into the one in front by having receivers in your headlights and transmitters in there. Japan's done a lot of work. The other person in Tiananmen Square was this guy, and he's done things transmitting from LED traffic lights to cars. So he's been using high-speed cameras and using clever modulation schemes where he switches on and off, so the pattern on your LED traffic light changes much higher frequency than you can ever visualize, but his high-speed cameras. So he's actually got these videos of real-time driving a car towards traffic light and detecting how far away it is and getting data from it. Steve Franilovic at McMaster University, he's done a lot of really interesting theoretical, he's a really good guy, does both theoretical and practical work. So one of the things that he's done outdoor, you know how you get mirage effects in hot weather? Well, that causes scintillation in free space optics. So what he did, he took the guts out of one of these, got the digital micromirror and controlled the digital micromirror so that as the scintillations changed, he controlled it so that all the light ended up on the photodetector, which is pretty neat. So yeah, What else is he? So he's also done. So I have only slightly mentioned it here, but you can transmit data from a screen and use a camera as a receiver. I had one postgraduate doing work on that. So then the question is, so now you can modulate in the spatial domain, and how do you do that in a way? Well, he came up with the idea of doing a spatial modulation technique based on OFDM, but conventional OFDM. Turns out that you can use our modulation technique, ASIC OFDM, in the spatial domain. So instead of modulating in time, you're modulating effectively across your screen, and you can do very well with that. Guy in China who invited us, he's doing lots of interesting things. So a couple of years ago, there was about 5 or 6 groups doing things. It's now, people have realized it's got lots of potential. So there's lots of other people. So basically, there's lots of really interesting things going on. A lot of it quite fundamental and practical to theoretical. At Monash, my little group is doing, we're punching above our weight by quite a long way, and doing quite a lot of the quite fundamental work. Okay, any questions?
Okay. You're using OFDM. I take it you're just feeding OFDM in at the baseband level.
Yeah. There's no. Well, that's. Yeah.
With the OFDM.
It turns out that OFDM is now the hot topic in optics, which is really interesting. So there are lots of different varieties of OFDM for different optical communication systems.
As with the radio system, you have a number of carriers within that OFDM.
Yeah. So
typically, would you have an optical baseband?
It depends on. I mean, it's the same rule as for anything else. There's a trade-off in OFDM between the amount. There's
Your bit rate and all that.
No. The really only one design choice is how many subcarriers you have. Because if you have more subcarriers, you end up with a longo symbol.
Yep.
And they've got this thing at the cyclic prefix at the beginning, which is a guard band, and so you want that to be as small as possible relative to the rest of your symbol, because you need one per symbol. But if you have lots and lots of subcarriers, it becomes much more sensitive to frequency offset.
Yeah.
So if you've not got your receiver well tuned,
But any digital system recovers the clock from the incoming data stream.
Yeah, but the frequency offset is more. Well, you've got Doppler as well.
Yeah.
So
with that system that was running 513 megabits.
Oh well, there's not. I don't know what she did there. It probably wouldn't matter that much. It would just be enough so that she could divide up the frequencies. So
typically be running a couple of thousand carriers.
Well, no, the data rate doesn't depend on the number of carriers.
No, but it depends on what modulation you've got on each carrier.
Yeah. So I don't know. Go back to. I don't. She probably. Where's the picture? Yeah, so I don't know how many she got, 1,000 or something. I mean, the constraint here, you don't actually need very much of a cyclic prefix for optical wireless, because the multipath delay spreads nothing, practically nothing.
But the
So
OFDM counteracts a lot of the fade.
yeah, but there isn't much fading anyway. So you don't. So really, they're using the OFDM so that they can put lots of data per subcarrier here, and a little bit down here. So the number.
Interesting is typically how many carriers.
Well, I think she's got thousands there. But the only reason is so that you can. Okay, if she only had 16 subcarriers, you couldn't vary the number of bits per subcarrier. It would be very clunky, so that she's got a smooth variation. So that one it doesn't. But you were also saying it's all at baseband. The optical fiber communications, the people are now doing coherent reception. So they've got a laser. The local oscillator at the receiver is a laser. So I thought it would be too hard to do that, because I'd have thought you needed such accurate frequency, but lasers are so accurate. So actually, the person at Melbourne University. So it was interesting. When optical OFDM hit the world, there were 3 groups doing it. There was Melbourne University, Monash University, and somewhere in Japan. So it was sort of the Australian technology briefly. But the guy at Melbourne Uni, a guy called Bill Shea, was doing the coherent optical OFDM, whereas I was looking at other aspects. So, yeah.
A question in relation to the in the blue part of the spectrum, is there a critical colour temperature in Kelvin that is the most efficient in that blue part of the spectrum?
Well, I mean, if you were only thinking about the communications, you'd be much better with infrared, because the photodetectors are much more sensitive at infrared, and you can, if you go infrared, you can filter out all the background visible light, which is much worse. So if you weren't using anything, but as far as the colour of the light, it's to do with what humans like. But there is another problem lurking there, that you depend on certain frequencies of blue light to know when it's morning and evening, and the LEDs don't have that colour of blue light, so you've got
And how much of a problem is 50 hertz interference?
none at all. You just get rid of that subcarrier.
Data rate's much, much.
So you just you get rid of. So I don't know whether she's done it there or not, but typically you would just throw away the bit at the bottom, just throw away the first couple of subcarriers, and it's so that the question about how many subcarriers, that's another thing. You always throw away the bottom bit, so you don't want interference from. Well, it's not actually 50 hertz; it's 100 hertz, because it's rectified by the time it comes out of your light.
Start running into critical eye problems too.
There's also the fact that the fluorescent light gives out kilohertz of interference, so you get rid of all the gunk at the bottom. Yeah. So.
I'm just curious about the physical aspect of modulating a light source LED of the normal typings for lighting, because they have an enormous capacitance. I mean, indium nitride has a huge dielectric constant.
Well, these are using standard. This is done using a standard off-the-shelf lighting LED.
We tried modulating standard white LED with power series, and we were lucky to get 50 kilohertz out of response, at least for the yellow phosphor.
Yes, I mean, there's
Curious as to how you overcome the capacitive effect. Are you driving with lots of power compared to what's coming?
well, she will have been. I haven't actually done these ones, but I've done similar things that get much higher frequencies just by well, most of my experiments are done with an arbitrary waveform generator and a digital sampling oscilloscope, which makes life very simple.
We found all sorts of problems, like the rise time on a typical white LED is much faster than the fall time.
Yeah.
So you have huge phase shifts involved.
I think it probably depends on how you're driving it. I mean, these are definitely done using standard lighting LEDs. So yeah.
So you're using ones with phosphor on them, or?
Yeah. I haven't. I mean, there are so many other people trying to build the world's highest, fastest thing. I've concentrated much more on the what's the modulation technique and what. But having said that, I did do some work with someone else at Melbourne, at Monash, on optical fibre communications, and we got some money and managed to get 500 kilometres of optical fibre, the first very high-speed Tektronix arbitrary waveform generator in the country, and a high-speed digital sampling oscilloscope. And I had lots of OFDM simulations going with, and the postgrad at the time got 10 gigabits per second over 400 kilometres within 2 weeks of getting the equipment. And the business manager said that doesn't sound very convincing, 10 gigabits per second. Everyone else seemed to be doing 20 gigabits per second. So I went back to postgraduate and said, you've got to get 20 gigabits per second out of it, and he did.
But the question is that how many dB down would that be compared to, I mean, surely there is a slow roll-off of the high frequency.
What, we're talking about optical fibre, or?
No, due to the
there's
physical operation.
Well, there is. That's why it's much lower signal to noise ratio here than here, So here I can't need to make it bigger, but she's using something like 1024 QAM at the top and BPSK at the bottom or something. She's got it's like your ADSL modem. Your ADSL modem uses huge constellations on the good carriers and something very simple.
What do you use as a detector? Because, as I understand it, silicon is far more sensitive to red and infrared than it is to blue. And if you're using the blue component to get the speed up, because presumably that's the exciter, not the phosphor, what do you use some special?
No, we've just been using standard. As I said, I haven't been going for the world speed record. I've been doing the smarts rather than the brute force. But there is no doubt. I mean, there are quite a lot of people around the world who've done it. And we've shown so. Yes, they're not very sensitive, but you've got lots of signal power there.
Yeah.
I think what you've got to remember too is the long haul optic fibre, and they have repeaters every 40 or 50 k.
Yeah, yes.
Data rate, like 140 megabit data rate is you can go out to about 80 k or something like that between repeaters. If you're going to 565. Back to about 40.
Yeah, the optical fibres have now got optical amplifiers in them. Up until now, the data rate and the backbone optical fibre has kept up with the internet just because communications engineers are getting cleverer and cleverer and cleverer.
Yeah, but the junction capacitance of a tiny injection laser firing into an optical fibre is far less than the junction capacitance of
Yeah,
like that thing right there. I would have thought there were problems with that.
There's people around the world doing it, and there's definitely standard lighting LEDs. I haven't. I'll go back and tell my group to try it out. But we got hundreds of megabits per second along a plastic optical fibre just using a green LED. It wasn't. Yeah.
I'll go to something that's a lot more simple. I'm just intrigued about why the attenuation was the fourth power rather than square law. Well, the square law with radio, it's simply because the field diminishes as a function of the area.
Yeah, well, so the field does diminish. Yeah.
So I can't understand how it goes to the fourth power.
So if the field diminishes as the square, then the power diminishes as the fourth power. The intensity diminishes as the fourth power.
The intensity of
Yeah. It's all smoke and mirrors. Yeah. So all this stuff you've ever, well, I don't know how much theoretical stuff you did, but the rules about how the energy per bit is all that matters doesn't. It's all, you've got to come up with different ways of measuring the whole thing. It's very peculiar. Yeah. Okay. Yeah. Go on.
Just a comment, just from what Chris was saying. Some of the obvious practical problems right at the, if you like, coal face, the LED itself. Seems to me there's a scope for an enormous amount of research going back the other way. In other words, redesigning the LEDs themselves.
Well, but I mean, one of the problems about how the whole of this gets commercialized is that it's spread across so many different industries. If you're trying to design a new radio system, then you speak to communications companies. But here, you're trying to design a communication system, and not even the light. So my understanding is that LEDs are produced by big companies in China, wherever, but light fittings are actually produced by quite small companies. So the whole thing's spread across. There's no one obvious place that you start to try, which is one of the reasons why I think the positioning is probably a better way to go, because you just need to be. If you can create something that stands alone that you plug in.
One of the things that gives you an advantage is you're basically not looking at a huge distance.
Yeah.
Basically from the roof to
Yeah, these 513 I think are only over a metre, so it's
There'd be an enormous, how should we say, market for a company that cottoned onto your ideas and started looking at redesigning their LEDs to accommodate
Yes.
your ideas, and I wouldn't mind betting that will happen.
Well, I mentioned Rick Roberts is from Intel. I'm pretty sure they're doing things with other big companies. But I mean, where do you start from? I mean,
Almost certainly.
no, but as an individual, I mean, it's
Yes.
It's, so, okay. Yeah.
Are there any standards emerging?
No, and actually, the article which I've got here, the one that I keep mentioning that we wrote about positioning. I've got something that tells me what it was. Oh, this special issue, and I've got the thing. If you actually look at, say, it was all about international standardization. I think I've probably got it here. So, it's in my bag. I'll dig it out afterwards. But basically, what happened was Rick Roberts, who was the guy from Intel, he was in the thing in China, and he said, everyone keeps saying OFDM's the best way to do that. Why was no one there? He was chairing the standard. Why was no one there championing OFDM? And I said, well, it's not, there's nothing in it for academics. You know, the last thing we want to do is be spending time. So I think they went away and thought about it, and he came up with the idea of making something in it for academics. So he, it was quite similar, a win-win situation. They had a special issue that was about standardization, and so we wanted, well, I decided that me with Amit Sakarioli and Adrian should aim to get the paper on visible light positioning in that special issue. So we scratched our heads and thought about what you wanted to have in a standardized thing and put all that together in a document. And well, he got the world's experts putting in a document, and we got a publication that keeps everyone happy. So it was so the standardization is another issue, and standardization of communications is a political nightmare because all the big companies want their patented technology in the standard so that they can charge you all lots of money to use it.
I presume that you wouldn't want to have a whole pile of data cables going to all your lights around the room, for instance. So I presume you'd be using like wireless receivers in the light, or
well, not necessarily.
Adjacent lights and like a local unit number to.
Well,
Is that part of the?
Well, there's so many unanswered. I mean, I'm basically cherry picking the interesting and easy ones because there's an open field at the moment. But that is a very good question. But there's the whole issue of how do you power the LEDs. I mean, it's pretty stupid that you've got the mains power coming to every LED, and then you've got some. So do you have it's a very good question. Do you have a DC power source, or can you have the same data? There's lots of unanswered questions, which is why I think visible light positioning is a whole lot easier to get going in a practical system, because you don't need to worry about all those things. The one idea is that your light bulb has a dip switch in the side that says how far you are from the corner of the room in XY coordinates, and the light just transmits that data. So yeah, so I reckon and that's why we specifically decided we were going all out to get, well, we were interested in the area anyway, but yeah. Okay, made you all time to go home? Yeah.
Pardon me if I missed something, but this is a two-way system with error correction back.
For the positioning or for the communication?
For the Wi-Fi, or is it just out?
Who knows? Well, at the moment, there's lots of open questions like that. Obviously, the transmission is from there by light, although people have also said you can use LEDs as receivers as well, but they're pretty useless receivers. So there are people have done papers on that, but my personal opinion, and the sort of opinion of most people, is that if visible light communications takes off, it will probably be light in the downlink and radio in the uplink. So, and most of the data rate on the downlink's usually much faster.
Just one major advantage that we found with through the atmosphere communication.
Yeah.
With light is that by putting a transmitting and receiving lens side by side, you get full duplex back and forth continuously.
Yeah.
You have to switch the transmitter.
Yeah, but people don't want light shining out of theirs. So there's,
Talking point-to-point links.
yeah, there's all sort. Well, yeah. I mean, it's like, you know, it's like radio 100 years ago. I mean, there's nobody knows the answers. So nobody knows is the answer. Yeah. But I mean, it seems to me that given that you can get, everyone wants bandwidth, and you've got transmitters in lots of prominent places that give you lots of data rate. Sometime in some way, someone's going to be using it for something. What that actually is yeah.
Bigger mirrors.
Bigger mirrors. Or more smoke. Yeah. Okay. Yeah. Thanks. Okay.
Thank you very much, Professor Armstrong. We've got the guest speaker has to draw the raffle ticket.
Oh, right, okay.
More work.
I'm sure I managed to do that.
Damien, reach in.
Okay. So. Do I have to read it out, or do I just give it to someone? There you go.
There we go.
No, I'll get her.
Level C22. Now, and I've got,
Okay, I forget.
it's a little banner, token of our appreciation.
Oh, okay, thank you very much. Thank you. And I did bring a few lenses along if people want to come and have a play. And I also mentioned there was a special issue if people wanted to. That's my only copy.
Communications of Australian.
No, it's IEEE communication. Oh.
Thank you very much. Conference are open tomorrow.